Welcome to Quadcopter Feedback Control, a presentation by Something Epic. I'm Brian Marsh.
I'm Matt Fouch.
I'm David Peck.
And I'm Tom.
Quadcopters are becoming increasingly more common for surveying areas after natural disasters. These machines are very useful for reaching remote areas which might be dangerous for people to go. One of the biggest problems for these drones is height control. So height can be difficult to control, particularly during landing, where if the machine comes in at too high a rate of speed, it can crash and damage the unit. Current quadcopters are affordable to NGOs, don't have adequate control systems. Both overshoot and non-zero steady-state errors can lead to the drone damage. Our objectives for this are to monitor the height in the feedback loop and to design a controller which can meet these desired specifications. We want to ensure that the controller results in a steady state with zero error and zero overshoot. We would like to also evaluate the characteristics to ensure that they are achieving desirable performance. So as the quadcopter lands, if it comes close to the ground and the system is designed with overshoot, you can get crashes. Our optimum control system will be a critically damped system. In a critically damped system, we would see a longer rise time and a longer settling time, but no overshoot, providing a safe landing. Now here's Tom to talk about the modeling of the system.
Thanks, Brian. So we began by first drawing our system's free body diagram. Then, to find our transfer function, we modeled our system as an impedance network, and using basic circuit analysis techniques, we found our final open loop transfer function, which was 1 over BS plus MS squared.
Thanks, Tom. Now we're going to look at the open loop stability of our system. In looking at the root locus of our open loop transfer function, our poles are in the left half plane and at zero, so it should be stable. However, if we consider the Routh-Horowitz test, we see that the S0 term becomes zero, indicating a lack of Bible stability. We can then plot the open loop step response, and because the open loop system is not Bible stable, given a unit step input, we are generating a constant force greater than gravity. Therefore, the quadcopter quickly reaches its terminal velocity because of the drag term B, and then increases its height at a constant rate towards infinity. The step response of our open loop system indicates that a small change in force is magnified in the behavior of our system. Due to this response, wind and change in mass have the potential to stabilize our final system and must be considered. Generally, landing is done in an open area where the force of wind is parallel to the ground, meaning that it applies a very small vertical force to the system. A change in mass, however, such as payload becoming unsecured, would be a similar disturbance, but the effects would be much greater with increased payload size. Both of these disturbances will result in unbounded responses when applied to the open loop system. However, a more accurate portrayal can be found by looking at the closed loop system. Here you see the Bode plots and step response plots for our uncontrolled system. And as mentioned earlier, our primary concern is the safety of the quadcopter during landing. This means that one of our primary design concerns is eliminating the overshoot that you can see present in our system. Because we want this soft landing, we'll be using a derivative controller to eliminate the overshoot by increasing the output as the downward velocity increases. Another significant consideration regarding our design would be the steady-state error, but as our system already has an integrator, it is already fixed to zero, and adding an additional integrator would only create overshoot. Other minor considerations in our design were the settling time and rise time. While not very important to solving our problem, it was still desirable to keep these characteristics in reasonable ranges so that you don't wind up waiting minutes for the quadcopter to land. I'll now let Matt talk about how we optimized our PD controller.
To test the system, we put it into Simulink with a fall height of 50 meters. Our model doesn't include gravity as a disturbance because it is constant. Our system outputs force relative to the force needed to hover. Guessing the coefficients of the PD controller got us close, but then we used the System Tuner tool built into Simulink to optimize the values. After getting our optimized values, we brought the transfer function and controller into SISO tool, where we then determined our gain margin to be infinite and our phase margin to be 90 degrees, plenty robust for this controller. And to give you the final evaluation of this system, Here's Brian again.
Thanks, Matt. So we put the values from our CISO tool optimization back into Simulink and did a secondary optimization tuning with a PD controller, which gave us a P value of 0.37, a D value of 1.745, and an N value of 40.7, which in turn gave us total evaluation of the system with a rise time found to be 5.85 seconds, a settling time within 1% of 11.09 seconds, and an overshoot of 0.16%, which is not zero, but is very, very small. We believe that a quadcopter would have sufficient landing gear to be able to absorb the impact from such a small overshoot.
So, to kind of wrap things up, we created a BIBO-stable system throughout this semester by first modeling the open system, which was unstable. From there, we closed the system and added the PD controller to decrease rise time and overshoot and create a stable system. Thank you.